Alright, welcome to 7.3 Volume as an Integral. We were talking in class about the idea of starting to look at shapes that were kind of rotational in a sense. And we talked about being able to break this up into several cross sections of area. And that's what we're going to look at today. And pardon this note section, but it wasn't uploading, so I had to take pictures of it. It looks really fabulous here. So the idea in class was we took a look at one slice of this thing and it said that it would have a cross-sectional shape of a circle. And for this unit, we're going to start off only talking about what happens if we take a part of a function and we rotate it around an axis. It's going to form a three-dimensional shape that's solid for now. And we're going to start off talking with the volume of a solid. And the volume of a solid of known integrable cross-section, and that literally means as you slice this thing up, what shape is the cross-section. You're just going to do the integral from A to B of the cross-sectional shape. Okay? And there's a nice little formula or a nice little process on how to find this volume. You're going to sketch the solid in a typical cross-section. You're going to see as we progress through this whole process. It's not always necessary, but for the visual people in the class, it's going to be helpful. Sorry guys, I'm literally sitting in a parking lot trying to record these notes. You're going to find a formula for the cross-sectional area, and for this particular section of notes, this is going to be circular. Okay, so we're doing cross-sections that are circles right now. You're going to find the limits of integration, and you're going to integrate in order to find the volume. Alright, so we're going to take a look at what happens if we've got a region between the graph of y equals 3 plus x times the cosine of x and the x-axis from an interval of -3 until 3. And we are going to go ahead and revolve this region about the x-axis. And it's going to generate a solid. And our job is to find the volume of that solid. So let's go ahead and show exactly what kind of a region we're talking about here. Let me see if I can do some highlighting for you. The region from -3 until 3, let me make that a little thicker here. Alright, so the region from -3 until 3, so this whole shaded region, right like that, that's the area that we are shading. And we're going to revolve that around the x-axis. And now, drawing skills, although a plus, are not necessary to do these problems. So let me see if I can get the pen tip that I need here. Okay, so if we're going to revolve this, and I always show which way I'm revolving, just like we talked about in class, that's going to spin this thing around and make kind of a circle. What I'm going to do is identify a couple of key points. If I was to take this point here and revolve this in a circle, it would come towards me and then it would spin back away from me, but either way it's going to come towards me and then it's going to spin back away from me and then it's going to be back behind over here. Some of you are like, what is she doing? I'm just trying to show that this thing is going to form a whole bunch of circles. If I take this point and revolve it towards me, it would come closer, and then it would dip further away, and then go back behind. The idea is that this shape that's being formed looks something kind of like that. And if you can imagine, it almost looks like the top of a chess piece, like a bishop or something like that. And if you don't play chess, maybe like a vase that doesn't have a hole in it. But either way, again, the whole drawing of the 3D shape isn't necessary to do these problems. The idea is realizing that since we are revolving, we are talking about forming a solid with a circular cross-section. Okay, so that's the main thing. If you walk out of here knowing, you got to know that. All right. The idea is that since this x-axis is our axis of rotation, the radius for each of those circular cross sections is going to be different depending where you are on the function. Okay, so for each circle the radius is different. Okay, but all of those radii are y values on the function of y equals 3 plus x times cosine of x. Okay, so the idea is, since we know that volume is the integral of area, of the cross-sectional area, our job is to figure out what's a formula for the cross-section then, for that area. Well, since it's circular, area equals pi r squared. And notice that since we're trying to integrate in terms of dx, right, we're trying to add all these circles from left to right, we need to come up with a way to relate the radius and the x values. Well, you just heard me say that since the function is defined as 3 plus x cosine of x, and the r value, the radius, is the y value at all the different points along -3 until 3, we can just substitute it in. The radius is the y value of the function. The square does not distribute, so we'll have pi r squared. And we're integrating this thing. The circle slices started at -3 and they go until +3, so that's what our bounds are. And this is a calculator allowed problem, so you can type that in exactly like you see it. And if you keep the pi within the integral, you'll get a decimal approximation. 63 point, actually this is in terms of pi, excuse me, 253 pi. So I think when I did this problem, pi is a constant, so I pulled that out to the front and then just tacked it on at the end for my final answer. So 63.253 pi would be the volume. And obviously I don't have units on this one, so I would just say units cubed, or you don't have to say anything at all. Okay, but the idea is that anywhere you slice this shape, because the shaded region has been rotated around the x-axis, the cross-section is going to be a circle, and we know that the area of a circle is pi r squared. From there, all we had to do was relate the radius to the actual function itself, because the radius is the y value on the function. Okay, and from there, it's just using your calculator. Okay, now for this problem, we are asked to find the volume of the solid generated by revolving. So there's your keyword, revolving. The region bounded by y equals rad x, which is going to be this guy, y equals rad x. And the lines y equals 1, so this is y equals rad x. We'll do a different color for this one. And we'll actually make this a little bit thinner here. Now we'll do the lines y equals 1 in green. And then x equals 4. Let's go ahead and do in purple. Alright, so the only region that's bounded by those three pieces is going to be this shaded region right in the middle. So this guy. Okay, so this is the area we're going to be revolving. But this time, we're asked to revolve it about the line y equals 1. So let me go back to a black pen here, and we'll shrink this guy up. Now, we're going to take that region and revolve it around this axis. So what that means is if I'm to start here and I revolve it, it doesn't go anywhere because it's right on the axis. If I was to start here and revolve it about, it would form like a circle looking thing like that. If I'm all the way over here, right, it's going to look something like that. And then if I'm at the end, I'm going to take it and revolve it, and it's going to be like that. It's going to be an even bigger circle. So again, depending on where you are, it's going to kind of form a bullet-looking shape. Okay? Now, some people in previous years have said, I don't know how to draw this thing. I don't get how you do it. Basically, if you want the easy answer, you will notice that the top part of the shaded region, oops, let me get a different color for you. The top part of the shaded region, right here, is symmetric about the axis of rotation. So if nothing else, just draw a reflection, and that's what the shape would look like. Okay? But again, the idea is you just want to see where your radius is. And this is our radius, it's right here. Okay, and how do we get that distance? Well, the radius is the y value of the blue minus the y value of the green. Okay, so top minus bottom. This should hopefully sound familiar. Volume equals the cross-sectional area integrated. Now, where are we starting the shaded region? Well, the shaded region actually starts back here over at 1. Well, let's call it a to b in the general formula. So the volume of this guy is going to be the integral from 1 until 4 of whatever we determine our cross-sectional area is. Again, because we are revolving, the cross-sectional area is going to be a circle. And I know that a equals pi r squared. And in this case, the radius is going to be the top y value of the blue minus the bottom y value of the green. Okay, top minus bottom. This is a theme that we've been doing, finding areas the entire time. The trick here, though, is that your area formula now becomes rad pi times rad x minus 1 quantity squared. The 2 does not distribute. So just make sure that you don't try to distribute that 2 and say that that's x minus 1, because that's not going to work. Okay, so I can change my volume now. It's going to be the integral from 1 to 4 of pi r squared. And again, if you want to pull the pi out to the front and then do the integral, that's absolutely fine. Okay, and if you get to that point, let me see if I can move this up a little bit, there we go. If you get to this point and you put this in on your calculators, your calculator is going to give you an answer for the integral part of 7 over 6. I still had a pi left over from before, so your final answer is going to be 7 pi over 6. Okay, now I'm sure you guys have a lot of questions for me. That's why I was trying to keep this a little bit shorter on the video note side of it. We're going to do lots of practice problems tomorrow, and I will see you then.